So we're going to do PID, but without the P, the I, or the D, because I tend to find them confusing. First thing we need to talk about is feedback. Feedback is where we take the process variable and we feed it back into the decision-making process. So in other words, we make a change and then we check to see whether the change was okay, and then based on that we make another change. So feedback feeds back. There can be positive or negative feedback. What we try and do is, what we do is we generate a thing called the error. And the error is the difference between what we want, which is the set point, and what we've got, which is the process variable. You have negative feedback. Negative feedback reduces the error. So in other words, negative feedback gets us closer to set point. So negative feedback is a good thing. You can also have what's called positive feedback. Now positive feedback increases the error, makes it worse. Positive feedback would be like trying to put a fire out using petrol. It's just making things worse. If you're looking for feedback control loops, the easiest place to look is in the mirror. Our body is full of all sorts of control loops that allow us to eat and drink, breathe, and generally walk around. So there's lots of negative feedback loops in our bodies, and they work really well, generally. The first control system really came about because of sheets, bed sheets. You see, what happened is they used to make bed sheets using looms, and the looms used to be driven by water wheels. Now, rivers don't really change speed very much during the course of the day, and so they work just fine. When they started making bed sheets using steam engines, a steam engine would change speed every time a bloke chucked another sort of shovel full of coal on it. So to try and control the speed of a steam engine, they invented a thing called the fly ball governor. Now the fly ball governor has got two balls, and it's driven by the steam engine, so that it spins round and round. As it spins round and round, the balls rise up. As the balls rise up, since they're attached by this linkage here to the steam valve, as the balls rise up, it closes the steam valve. What this means is that the steam engine then slows down, which means that the balls drop down a little bit, which opens the steam valve, which means the steam engine speeds back up. With a fly ball governor, you could maintain a steam engine at a set speed. It did tend to oscillate a little bit up and down as the speed changed, because it's a pendulum, and any pendulum tends to oscillate. So to overcome its tendency to oscillate, what they used to do was they would just tighten up the nuts here and stiffen the whole thing up. That would stop it oscillating so much. The problem with tightening up the nuts too much was that it never quite got to set point. You see, you'd have a set point, there'd be the set point, and it would come up to nearly the set point, but not quite get there because it was just a bit stuck. So to get it to actual set point, anybody got any ideas what they would do? What the engineer in charge of the steam engine would do to get it to set point? Absolutely right. He would hit it with a spanner. Now that's important to remember because that's actually how a modern PLC works. It has an I term, and the I term is equivalent to hitting it with a spanner every now and then. We'll be coming to that. Controllers got a bit better, especially when they started using pneumatic, which is compressed air. Started using pneumatic for signaling. And they discovered that they could make controllers using pneumatics, using clever bellows and pulleys and air blowing out of places and reverse acting relays and springs and all sorts of good stuff. And they could make more and more complicated controllers until really you had to be some sort of clockmaker in order to work on this thing. You had bellows within bellows and restrictors that were variable and all sorts of things and pulleys and little cuckoos that would pop out. They knew exactly how everything would respond. Around about, I think, 1780 or is it 1870? I forget. A man called Lagrange came up with some equations that described how control should work. And Lagrange described how things should happen. He said it should have a P term. P is proportional. It should have a P term, which meant that if it went out by, say, 5, we would open the valve by 3. If it went out by 10, we'd open the valve by 6. That was proportional. It should have an integral. An integral part. And the integral part meant if it had been out for a long time, then we'd clonk it occasionally, like hitting it with a spanner. And it should have a derivative part. And the derivative part said, if it suddenly changes, we need to suddenly back it off. And these are the 3 parts that Lagrange described, and he called it the PID response, a PID control. They could use, around about the 80s, 70s and 80s, they discovered they could use electronics instead of pneumatics. And they could use op-amps to build clever little things that would do proportional, derivative and integral. The equations that Lagrange came up with were these. There are 2 versions of the PID equation, what's called the parallel version and what's called the series version. The top one is the parallel version. The diagram below explains that. And the bottom one is the series equation. These are the equations that Lagrange came up with. And he said, right, these equations have got 3 parts. There's a P part. There's the P part. There's an integral part there. That's the integral part. And there is a D part. Just here. So, we are integrating with respect to t from 0 time to present time. Then we are differentiating with respect to t, a function of the error. Back in the olden days, you used to have to spend a lot of time deriving all these equations and working things out and proving it. And you actually had to know, well, calculus, in order to be able to do this junk. Now, one thing has changed. These equations rely on the fact that the error thing here, is what's called a continuous function. So in other words, we're continuously looking at the process variable. We're always looking at the process variable. We're not sampling the process variable, we are continuously looking at the process variable. Now let me ask you, with a PLC, and a PLC uses an analog to digital converter, or an ADC, does an ADC continuously look at the signal, or does it sample the signal? You're right. An ADC samples the signal. Now, that's a bit of a problem because these PID equations that old Lagrange came up with only work for continuous functions. So, all of this stuff has gone. None of it is relevant anymore because, well, we don't use those equations anymore, so there's no point in teaching you them. At this point, the PLC manufacturers said, oh, well, that's no big deal. All we'll do is we'll take the PID equations and we'll run them through a thing called the Laplace transform. And a Laplace transform allows you to change continuous functions into sample functions. So they took the PID equations and they ran them through a Laplace transform. And they tried that on their control systems. The only problem with that was it didn't work very well. It didn't control very well. So, all of the manufacturers then decided to go their own way. So what they did is they had the PID equations, which they Laplace transformed, and that didn't work. So then they took those equations, and each manufacturer pretty well went his own way until we have what's called the A, B, C, D, and E versions of the PID equation. And in many cases, the equation itself is a secret. They don't want to tell anybody else what the equation is. The upshot of all this is that we don't actually know truthfully what equation any particular PLC is using. So my thinking on the subject is, I don't know what the equations are. I'm not going to teach you what they are. Instead, I'm going to teach you how to work them, or how to calculate the values you need. It's kind of the difference between teaching you how a car engine works and teaching you how to drive. I'm going to teach you how to drive because I don't know how the engine works on these things. Right. And the way this works is remarkably similar to the way you drive. So, there's a few things I like to go through. Right. You're sitting at the lights, and you look up, you see a speed sign, and the speed sign says 60 kilometers an hour. Now that's the set point. That's your target. The lights go green. Okay, you put your foot down. Now you put your foot down a distance which is based on your experience as a driver. You know that that's roughly going to get you to set point. It's not going to get you bang on to set point unless you're lucky. It's going to roughly get you to set point. Now I call that a ballpark move, which gets you somewhere nearby. And it's going to be different depending on whether the road's wet or you're on an incline or whatever. But it's going to get you somewhere nearby. You then zip down the road and you check your speedo. And then you make a small correction move, which I call a nudge. Now, that is exactly how a PLC works. A PLC doesn't drive along constantly looking at the speedo. A PLC samples the speedo and makes nudges. So, this is the P move. This is the I move, where you're going to sample and nudge, sample and nudge, sample and nudge. That's how you drive as you're going down the road. You sample and nudge, sample and nudge. Now you're going down the road a little bit more and you see a speed camera. Now irrespective of what speed you're doing, because you've seen a speed camera, you're going to take your foot off the accelerator. That's what I call the panic move. That's kind of what the D term does, the derivative term. So we have these three terms, P, I, and D, which I like to call ballpark, nudge, and panic, because that's pretty well what they do. So ballpark, nudge, and panic, they're three adjusters. They're three boxes in a PLC, and we have to put numbers in those 3 boxes. And by putting numbers in those 3 boxes, we will tune the control system and get it to control nicely. PID tuning is all about finding the numbers we need to put in those boxes. The first one, ballpark. It gets you somewhere near to your set point. Now, feedback causes oscillation. If you put too much of anything in, you go into oscillation. Too much P term, and we go into oscillation. So when we're adding the P term, if that's my set point, I add a little bit of P, and it goes up a little bit. I add a little bit more P, and it gets nearer to set point. I'll just use a different colour. I'll add a little bit more P, and I'm getting nearer to set point. Looks like I'm going quite well. I add just a little bit more P, and oh dear, off she goes and oscillates. That's how it works. The nudge thing, the I term, what this does is, there's my set point. If I've just got my P in, then it will get somewhere near but not quite get there. The nudge term is a bit like the engineer coming along and hitting it with a spanner. What this does is it makes it get there. So it puts a slope on that line. And a bit more of this puts a bit more of a slope on that line. But too much, and we're off into oscillation again. Now what the D term does is, if there's a sudden change in things, so if the speed is hanging along happily like that, and then suddenly it makes a huge change, what the D term will do is make a huge change back all of a sudden. It makes panic moves based on sudden changes. Problems we have with so-called PID tuning is, whose standard are we exactly going to use? Manufacturers can't agree on anything. They can't agree what they're going to call things. Sometimes you have values that if you increase them, makes, for instance, a P term more effective. Sometimes decreasing the value makes it more effective. Here's some examples. First I'll look at P terms. Here's my P terms. If your P term is called some kind of gain, so if it's called a proportional gain or gain, then it's making it bigger makes it more effective. So anything that's called a gain, making it bigger makes it more effective. If, on the other hand, the P term is called a band, a proportional band, making it smaller makes it more effective. The relationship between the two is this equation here. Proportional band equals 100 divided by proportional gain. Now, with the I term, if you have a thing called an integral gain, then, once again, making a gain bigger makes it more effective. If it's called a time, making a time smaller makes it more effective. The way I think of this is, you've got a man, the I term is equivalent to somebody hitting it with a spanner. By altering the gain, you can alter how hard he hits it. By altering the time, you alter the interval between when he hits it. So, by making the time smaller, you get him to hit it more often. Now the D term, if it's called a gain, making it bigger makes it more effective, and if it's called a time, making it smaller makes it more effective. The relationship between times and gains is just a reciprocal relationship. It's just 1 over it. The sort of equations that typically PLCs use, proportional gain, reset time, and derivative time. The equations that we're going to be using will calculate proportional gain, reset time, and derivative time. If your PLC uses an integral gain or a derivative gain or proportional band, you have to do the conversion. Now, one thing I cannot emphasize enough is that feedback causes oscillation. Feedback basically wants to oscillate. Any control system that has feedback, the first thing it wants to do is oscillate. It's happy when it's oscillating. When we're tuning control systems, our job is to find the very rare number of values that will stop it oscillating. And it's a bit of a trick to find these values, honestly. When it comes to the naming of names and the sort of terms we use, it's all based on study of oscillating systems. Probably the most familiar oscillating system to you is the suspension on your car. The suspension on your car, if you bounce it, it bounces a couple of times and stops bouncing. If you ever wonder about what any of the terms we are using, what they mean, just think, what would this mean if it was to do with my car suspension? We use terms like damping. Well, damping on cars that's what the shock absorbers do. We use terms like bumps. Well, a bump for car suspension is a bump. So if you're ever unsure what a word means or what we mean by something, just think, what would this mean in terms of car suspension? And you can pretty well get the hang of it. In addition, we tend to say that good control, well, with car suspension, good car suspension, if you go and bang your car, the corner of your car, it should bounce down, bounce up, and then settle down. That is what we call good car suspension. That's also what we call good control. With good control, you get a little bit of an overshoot, you get an undershoot, and then it settles down. So that's good control. If you ever want to know if control is good, then just compare it to your car suspension. If you have a four-wheel drive, you bang the thing, and it takes ages to settle back down. It doesn't overshoot. If you have an American car, they have very soft suspension. And an American car, it would go bounce, 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 puke. Because they like soft suspension. When it comes to PID control, sometimes we use P. Sometimes we use P only. Pure proportional control. Sometimes we use P and I. And on very, very, very rare occasions, we would use P, I, and D. The first thing we'll need to do is decide which type of control we're going to use. Whether you're going to use pure P, whether you're going to use P and I, or whether you're going to use P, I, and D. So, a couple of questions. Let's take a system which is entirely predictable. Let's say an AC motor. An AC motor running at 50 Hertz, a 4-pole AC motor running at 50 Hertz would be going roughly what speed? How many RPM? Okay, round about 1500. Let's call it 1440 because I've got a little bit of slip there. So if I'm going 1440 RPM at 50 Hertz, what would I be doing at 25 Hertz? $720. Now, barring a fault, barring somebody so overloading the motor that it actually starts to stall or single phasing, in a normal course of operations, will there be any variation at all in those speeds? No, they won't. It's an entirely predictable system. If I want to get 720 Hertz, I give it 720 RPM, I give it 25 Hertz. 25 Hertz, it runs at half the speed. It is totally predictable. In this case, what I would use is pure proportional control. It's completely predictable. I would use pure proportional control, and I wouldn't use feedback. I don't need feedback, and if I use feedback, the most likely thing that's going to happen is that it will oscillate, because feedback causes oscillation. So if I have a completely predictable control system, I use P only. Now, in terms of my little cone, this is equivalent to I'm pushing my cone. So I'm pushing my cone. If I push my cone for half a second on a flat surface, flat horizontal surface, it will travel a certain distance. And it will always travel the same distance for every half second of pushing. And that's just how it is. Now, if I have a system which is slightly less predictable, such as my cone lying on its side, if I have a slightly less predictable system, I know that if I push it for half a second, it will move a certain distance. But if there are imperfections in the table, it might move, and it might roll back a little bit, or it might roll forward a little bit more. In this case, I need P and I. The P part pushes it a certain distance, say half a second's push. The I part then uses the feedback and monitors it and nudges, monitors and nudges. That way, if I need to get the cone exactly onto that line there, I'll push it for a big P term, and then I'm going to look at it and nudge it backwards and forwards until I exactly get it on that line. Now, I'm using feedback, which means it's liable to oscillate. But I'm using an I term, and the I term should nudge me bang onto that set point. So when I have something which is slightly unstable, not totally predictable, I use the P and I. If I have a system which is what's called inherently unstable, an inherently unstable system, which when it starts to collapse, continues to collapse at a faster and faster rate. So this is like a cone standing on its tip. If I have an inherently unstable system, I need to use the D term. What the D term does is, as soon as it starts falling, it gives it a quick shove in the opposite direction. The D term is what I call the panic term. It makes panicky moves to get the thing standing up. There's not really many places you might use this. The only place I can think of that you'd use this regularly is on something like rocket control. You see, if you think about it, with a rocket engine, the rocket is at the wrong end of the thing. You're having to balance a rocket on the end of its engine. It's very hard to get a rocket to stay up. And if you've seen the videos of early rockets, well, they didn't. So vector control on a rocket uses PID. But truth be told, this is hardly ever used. Hardly ever used. We hardly ever use the D term. We use the P and I terms 99.99% of the control loops you will see. You'll use P and I. 99.99% of the loops are pretty predictable, but not totally. In my career, and I've been doing this for a little while, I have used D term twice. and they were both very unusual circumstances. Once was on a vacuum separator, which when it started to empty, you could very quickly lose the vacuum seal, so it had to be filled up quickly. And the second time was when I was doing pressure control on a massive, massive fan that would just, well, run away with itself, basically. So you hardly ever use the D term.